The next step in working with polynomials so we just saw adding, subtracting, and multiplication of polynomials. The next step is going to be to undo the multiplication. Now you might think that means division, but it actually doesn't. It's a variation of division. It's called factoring. And so think about, we did this with numbers. I'm sure you did this with numbers, when you were learning basic arithmetic. But for instance, the number 14, right? So you know that 2 times 7, when you learned multiplication, is equal to 14. But now you can factor. So that is, if you started with the number 14, the question is, what does it break apart into? What are its factors? And the answers would be 2 and 7. Okay? And you can do this with any number that's a composite number. The only exception, if you have prime numbers, you can't really break it down unless you had 1 in itself. But generally speaking, if you had a composite number, you could factor it or break it apart into the things that that multiply to it. Okay, and so that's essentially what we're going to do. But now we're going to do that with polynomials. We just learned about multiplying polynomials, so we're going to learn about breaking them back apart and calling it factoring. Okay, and it's called factoring because the two expressions, or the two numbers that multiply together, are called factors. Okay, so just kind of a basic example. Think about the multiplying idea again. It really comes down to the distributive property. And if you think about just a basic one, distributing 2 times x plus 7, when you distribute that, you multiply the 2 in to each term, and then both terms end up with a factor of 2 in them, right? So there's a 2x and this is a 2 times 7 essentially. Well, to reverse that process is called factoring, obviously. And to reverse that, you would be starting with the final polynomial, the product, and trying to factor and determine what the two polynomials were that you got it from, okay? In our case, it's going to be a monomial and a binomial. So what ends up happening is, if you look at the two terms and notice that they have a common factor of 2, then you undistribute, or we call factor it out, okay? You pull out the 2, that was the common factor, and then instead of multiplying this way, you divide by that 2. So if I divided 2x by 2, I just get x. And if I divided 14 by 2, I just get 7. Okay? So instead of distributing in, you're dividing out. Okay? So it's kind of a reverse process there. And of course, we could do this with far more complicated polynomials. You could make the terms more complicated. You could even add terms and make 3 or 4 terms. As long as they all have the same factor, you can factor out or divide out. Okay, I'll call it factor out though. So for instance, if we had 5x to the third plus 15x squared minus 35x, well, here these 3 terms all have something in common. They all obviously have a 5 in common to the number. They also have a factor of x in common. And so when you have more than one factor, you can combine them, and it's what we call the greatest common factor. It's the product of all the common factors between the terms. And so here, the greatest common factor, or what I'm going to write as GCF, greatest common factor, is 5x in this example. Okay. In the previous example, the greatest common factor was just the 2. Okay. So here, I'm going to factor out the 5x, I'm going to actually do the factoring. And so essentially we're going to divide each of these terms by 5x. Or you could also think of it as leave the remaining factors if you removed a 5 and an x. So here I have a 5 and an x cubed. If I remove the 5, remove one of the x's, the 5 is gone and I'm left with just 2 of the x's, so I have x squared. Okay, essentially you're subtracting the powers. If I have 15x squared, I want to remove a 5, I get a 3. And if I remove one of the x's, I still have 1 left because I started with 2. And on the last term, the minus will stay. When I divide out the 5, I get a 7 from the 35. And when I divide out the x, well, there's no more x. There was only 1 to start, and if I pull that 1 out, I don't have any more left. Okay, and that's it. So again, it's a division, particularly when you look at the numbers you're dividing, right? So 5 goes into 5 once, 5 goes into 15 3 times, and 5 goes into negative 35 negative 7 times. With the variables you're subtracting, because division of variables is a subtraction of the exponents, right? So 3 minus 1 is 2, 2 minus 1 is 1, and 1 minus 1 is 0, nothing, okay? So anyway, you get your division and your subtraction going on, and that's how we pull out or factor out a greatest common factor. Now again, this can also work when you start to add more variables. So we'll get another example in here. Let's take a look at 49. Oh, I want to change colors here, so it's not so confusing. Let's do 49x to the 4th, y to the 3rd, z to the 2nd. Oh no, I'm sorry, z to the 5th. I read that wrong. Z to the 5th. Minus 70 x to the 3rd, y to the 5th, z to the 4th, plus 35 x to the 4th, y to the 4th, z to the 3rd. Okay. So that's quite a bit longer, right? More variables, more powers, larger numbers, all that stuff. But again, we can pull out a greatest common factor. Get rid of some of this stuff on the left here so I have more space. So I look at I'm gonna just focus one part at a time, one factor at a time. So look at the constant, or the coefficient. You've got 49, 70, and 35. What do they have in common? Well, 49 is 7 times 7. This is 7 times 10, 7 times 5. They all have a 7 in common, right? In fact, it's the largest number that they all have in common. So my GCF is 7, or has a 7 in it. Now if I look at the x's, I have x to the 4th, x to the 3rd, and x to the 4th. Well, they all have at least 3 x's, right? 3 is the lowest number, the lowest power, and so that's the one they have in common, right? This has 4 x's, x times x times x times x. Yeah, this one is 3x times x times x, and so forth. And so you want the lowest number, lowest power, because that's what they all have, okay? So I want x to the 3rd included in my greatest common factor. Now look at the y's. So again, applying that principle, the smallest power is what we want to look for. So here's a 3, a 5, and a 4. That means they all have at least 3. So it's y to the 3rd comes out. And then the z has a 5, a 4, and a 3. So we'll take a 3 out of that one as well, because that's the smallest power. Then I can divide all my coefficients and subtract all my powers from what's out here, and I'll get the remaining factors that are on the inside. Okay, so 49 divided by 7 is 7. Then I do my subtractions. 4 minus 3 is 1, so that's just an x. 3 minus 3 is 0, so I don't need the y. 5 minus 3 is 2, so I get a z squared. Then I have negative 70 divided by 7 is negative 10. 3 minus 3 is 0, so I don't need the x's. 5 minus 3 is 2, so I have y squared. 4 minus 3 is 1, so I still have a z in there. Positive 35 divided by 7 is 5, so I have a plus 5. On the powers, 4 minus 3 is 1, so I still have an x. 4 minus 3 again is 1, so I still have a y. And 3 minus 3, well, that's 0, so I don't need the z in there. Okay, and so then I've covered everything. I've covered all my bases. I've got all my coefficients divided down and all my powers subtracted out. Okay, and you can always recheck these or double check these simply by redistributing the greatest common factor into the set of parentheses. And if you did that, you redistribute, you multiply, you get 49, then you add your powers. 3 and 1 makes 4, 3 and nothing makes 3, and 3 and 2 makes 5. And so you can do that and just double check, make sure you didn't miss anything, okay?